Okay, lovely people. What do I have for you this AM? Is it this AM? This PM? Okay. So, iron magnesium oxide. If you look up, what is the highest specific gravity? Iron magnesium oxide and heavy metals are the lowest. I'm sorry, and heavy metals, and the lowest are alkalis, silicon, water. Well, what does this have to do with anything that I normally talk about? Let's scroll to the left here. Let's go back a page. That didn't quite work. Shoot. That didn't work out like I wanted it to. Let's go this way again. Oh well. That didn't work out. Let's see. So go here. And it would be here. Oh, forget that. I want you guys, some Stadia guys, some okay, so how do I do this? Okay. What's the specific gravity of half-inch pea gravel? Okay, so it turns out pea gravel weighs more than water. Okay, got it. Check. Okay, what is specific gravity of Portland cement? Portland cement. Oh, 3.15. Okay, so it's heavier than water. So specific gravity of water again. Specific gravity of sand. 2.65 and 2.67. Okay. All right. So specific gravity of water. Oh, that's our base. That's a 1. Okay, got it. So 1 is, if we think of it as being lighter and heavier, the bigger numbers being heavier, we have the 1 is the water. Now we think of a concrete mix, right? So imagine your sand, your mixture. For you contractors and engineers out there, your mixture. We're going to talk about bleed water now. Why does it happen? Well, bleed water is that magical thing that it's a concrete reaction people believe, and the water just goes to the surface. Well, you're an idiot. All right? You're an idiot. You know how I want you to remember it. So this is why I call you an idiot now, because I want you to go, oh yeah. I want you not to think of it as negative, but I want you to think of, wow, it's so simple when you explain it that way. Yes. Okay, so water is a 1, and we're displacing. When we make the mix, we made like a cake, a mix, right? And then we put it down on the ground, whether it be on a vapor barrier, stone, sand, whatever you put it on. It depends, because some of that will displace and get sucked in by the temperature below. Get wicks down into the with drying effect of the water. If you put it on like a hot day and the ground is very hot, some of that will get wicked down that direction, and the majority of it, or a lot of it, will get wicked off off the top through the sun evaporation. And you could pretty much judge that by spraying the ground with water, and if it doesn't wick away, well then you don't have a ground temperature issue. And it's going to be from there. And you know that also if you put down plastic, it's not going to penetrate. So all your displacement, this is why it takes longer for bleed water to take place under plastic, because of what I'm going to explain to you, is that imagine a glass cooking dish, or the Tupperware, the big one, square, rectangle, okay? So make your concrete mix up. You're going to have your sand. We're just going to limit this. We can use fly ash if you like, but you're going to have sand. You're going to have stone, whatever size you choose. You're going to have your Portland cement. You're going to have your water. Remember your water and your fly ash. So let's see. So your water's your 1. So specific gravity of fly ash. So they add fly ash into this stuff too. Let's do Portland. Let's let that one pop up. So there's your 3-1, right? And then let's do pea gravel. So there's 3-1. There is, we did that one already. So we know that the pea gravel's more dense than the Portland. You just know that through common sense, right? And the 3/4 stone is even more dense than the pea gravel. So imagine that you make this soup up, this delicious soup. You stir it up, and you're making the soup. What happens when you stir up the soup? Well, you're intermixing the ingredients, and that's the best time. You dip your ladle in and take an even proportionate amount of the chunks and the fluid out. But if you let the soup sit there, what's going to happen? Just like your concrete, all your fluids are going to be at the top of the soup, and when you dip your ladle in, you're going to have all the water, the fluids up top, and your solids are down the bottom, your potatoes, etc. That's the same thing you're doing with, but then you mix it up and you can grab it. That's the same thing you're doing with the Portland cement with your concrete mix. It's mixed up in the truck, it's thrown into the ground, and just like your soup, it takes a while for the specific gravity, the weight, the density of each one to find equilibrium. So sometimes you can get, say, a half inch, not quite, maybe about a quarter inch of sand to support the load of the stone that has a higher specific gravity than above it. So it's finding equilibrium. So the stone is, say it's a 3.15, let's say. The sand's a 3.15. And let's say you can stack up a quarter inch of that. It has a compressive ability at that point to resist, say, a stone that's above it. And a stone, a pea stone, a half inch, quarter inch, half inch pea stone. And if you put two stones on top of it, well, now it can't resist that weight of it, and that quarter inch now gets compressed down to maybe, say, 1/8 of an inch before it can now resist the load of the two stones above it. So you can imagine how this is a whole entire soup, multiple tens of thousands of locations in your entire pad are going through this specific gravity equilibrium evolution to get to equilibrium. And as the Portland stiffens up, it also stiffens up. It makes stronger the sand combination, which then holds the stone up even more, and it locks in the surface area of the stone also. But the reaction is going to be with that sand. It's going to start binding and making a diluted paste, a concrete paste, the strength. And of all that, the water does the activation, but of all that, the water is a 1 still, and it's going to want to, as your soup, heavier materials segregate to the bottom, your 1 specific gravity goes to the top, your soup, right? Just like in your soup, your big bowl of soup, your big bucket of soup, your big pot of soup, the water gets pushed to the top. Not really. The other stuff goes to the bottom. The water just goes to the top because of the specific gravity. Equilibrium, I always tell you. Equilibrium, guys, can explain everything in the world. It explains everything that's wrong. It's equilibrium. Everything that you think is, that you find wrong, just that you think is wrong, it's really just equilibrium taking place. When you see a fracture happen or a break happen, it's still equilibrium taking place. The pressure exceeded it. To release the pressure to get equilibrium, and had to break free, a fracture. Now, specific gravity of fly ash. So this is an interesting when they start adding these different deals in there. A fly ash is still greater than a 1, but you can see where it will want to get a 2-1, 3-0. It's very interesting, isn't it? And there's your fly ash, and so it depends on how much time it has to start doing this settlement. How long does it take for the soup to go down there? And I state that you want to get the mixture sort of in equilibrium so it doesn't have too much displacement going on, where a heavier stone is not trying to push its way down. So I frankly don't like the larger stone, the 3/4 stone, the angular stone. I'm a pea gravel person. It's round. It doesn't have the sharp edges that will want to do that. Let me run the cat off. She's trying. Yeah. What the hell? Sorry, guys. Got it. I think I just messed up the video. I've got to hang up the video and we'll go from here. I'll add to this. Bye.